math behind animal migration. Tracking methods. GPS tags. GPS tags are the primary instrument used by researchers to measure and track populations. GPS tags are fantastic because you can figure out where an animal is anywhere in the world at any time of the day. Banding and recapture. Bands or metal rings are oftentimes placed on birds' feet as a way to track them, oftentimes because GPS tags are too big or too expensive for a research project. The only downside to this is that they can oftentimes be lost and must be recovered for the population to be tracked and to estimate population numbers.
Estimating populations using statistics. So with the information from capture and recapture methods, we can estimate population sizes, and we want to be able to do this so that we know how environmental factors impact populations. The most common way to do this is by using the Peterson method. This method creates a ratio, or rather a proportion, between the number of marked and unmarked animals captured. We can then use this proportion to estimate the entire population of such species. Later on, we can also use this proportion in confidence intervals to see how accurate our estimate was. The formula used in the Peterson method is as follows. P equals m times c all divided by r, and down below the variables are defined. And as I said, the formula creates a proportion which concludes that the proportion of animals captured in the second session is the same as the proportion of the total marked animals in the total population. And as I mentioned before, we can use confidence intervals with our estimate from the Peterson method to see how accurate our calculations were. The formula used for confidence intervals is p hat plus or minus z star times the square root of p hat times 1 minus p hat all over n. And the variables in the formula are defined down below. Now, to compute confidence intervals, we also have to have certain requirements that are listed down below. And to clarify, the first requirement is a simple random sample, meaning that the sample we used for capture and recapture methods has to be random, and that also accounts for independence, so that we don't count an individual animal twice.
Why animals move and migrate?
So, a basic overview of why animals migrate. There are many factors that impact this, but we're going to focus on heat, wind patterns, magnetic fields, reinforcements from the environment, seasons, and some other environmental covariates, and the mathematical concepts behind each of these. So it's also important to keep in mind that these are just models, so this isn't going to be the case every single time.
Pictured in the top right, we have the heat equation, which models how animals move about their terrain along the path of least resistance. U is the given temperature, and T is time. A would be thermal diffusivity, which is the rate at which heat can spread through a medium related to the inverse of thermal resistance. The steady state solution is the heat equation expanded out. With these two equations, we can model a graph that predicts outgoing routes that animals are most likely to travel on. There's an example of that in the bottom left, where the dark black circle is the epicenter and the white lines are the most probable routes that animals would migrate on.
So for magnetic navigation, there is going to be pigeon migration.
The core of the Earth gives off a magnetic field that leaves the South Pole and re-enters at the North Pole. Certain animals, especially birds, have a magnetic sense which allows them to detect where they are at every time of the day using the angle at which this magnetic field enters the Earth. Infant pigeons adopt a nest that they stay in for the rest of their life using visual landmarks, smell, but most importantly, magnetic navigation. When these magnetic fields are disrupted by putting magnetic coils around a pigeon's head, gluing magnets to their necks, or making a pigeon travel through a magnetic anomaly, they can't find their way back to their nest. This shows how important magnetic navigation is in pigeons.
So loggerhead sea turtles also use magnetic navigation. So if you can see, those are the routes that they travel in the picture below. And so it has been found that turtles with similar genetic compositions are going to occupy similar magnetic fields in the islands on those magnetic fields. So, as you can see, there is a most statistically relevant correlation between magnetic distance, so which magnetic field, and genetic differentiation, whereas with environmental similarities and geographic similarities, there is less statistically relevant correlation. So to sum it up, in the study, it was found that the difference between the magnetic fields at 2 nesting beaches was a strong predictor of the genetic differentiation between the turtle populations that nest in the 2 locations, regardless of the geographic proximity of the nesting beaches or their environmental similarities. So another method of migration is wind optimization, and this is observed in birds. So when traveling, birds seldom travel from just point A to point B in a straight line. They try to take the most wind optimal route. So by taking the most wind optimal route, birds on average save 26% of the time that it would have taken them to just travel in a straight line. So this is calculated using iterative wind optimization, in which scientists start from a gray node that you can see in each one of the timestamps and iteratively calculate the most wind optimal route from that node. So the smaller black nodes, if you trace them back to the original gray, that will be the most wind optimal route. And by calculating ground speed, we can do this. So we are given 3 variables. We are given the wind support, crosswind, and airspeed. And so crosswind is going to be blowing across the bird's body, so pushing it sideways. And using this equation, we can calculate ground speed across a hexagonal grid across the world. And that's what this would look like. And so we can also calculate survival rates. So in the graph, you can see that the highest rate of survival is actually not going to be a straight line. That dotted straight line has a pretty low survival rate, but the most wind optimal route has a higher survival rate, and it is actually kind of curved and does not go in a straight line. And this can be used calculating migration, mortality, and travel time to calculate that survival rate. And here are some more visuals about that. And then for movements across the home range, this is not necessarily migration, but it is still animal movement. And so using the concept of quantitative hedonism, animals are going to move and allocate their responses towards something that gives them more positive feedback. And this is going to be proportional. So in the most basic example, there's a source A and a source B. And source A is going to provide 100% rate of reinforcement, source B 50. And from that, animals are going to be twice as likely to allocate their responses towards source A. So in baboons, troop activity is going to represent a sort of circadian rhythm when the troops' tracks are plotted against time of day. So baboons spread out from their sleeping areas and their sleeping trees and reach maximum distance from that area around noon, so midday. And baboons, as they're doing this, are going to allocate their responses according to this concept of quantitative hedonism. For example, choosing which oases to stop at. And this is an example of what a circadian rhythm might look like. This is not actually the baboon example. This is just an example of the pattern that it displays.
Other factors affecting migration, Serengeti Lion Project. We had the honor to interview Dr. Stacy Hepler, a professor at Wake Forest, who's been working with the Serengeti Lion Project since 2015. The Serengeti Lion Project started in the 60s, observing 24 prides of lions in the Serengeti National Park, but has been expanded to study all animals in Serengeti and how they interact with each other and their environments. Researchers have set up 225 cameras, mostly on trees, but some on posts 1.5 miles apart around the Serengeti, that take photos when there's a change in ambient temperature. These millions of photos a year are then cataloged by volunteers who see if there are multiple species interacting and what the species were doing in the photo. This data is turned into binary inputs that overlaid with data from MODIS, which runs on 16-day cycles and outputs a 250 by 250 meter grid, can be modeled to predict where certain species are at every time of the year. With this data, scientists can study why these animals in the Serengeti are where they are. Factors that affect animal migration in the Serengeti include bushfire, water proximity, greenness, and even termite mounds. Some math behind Serengeti migration. First, let y represent the binary input, 0 if the animal is not present, 1 if it is present. We can then use this with different environmental covariates to find p, the probability that the animal is going to be in a certain location. Here's another similar equation, but psi is the probability and z is the binary inputs, but the same environmental covariates such as greenness, distance from water, if there was a recent fire, etc. This is an imperfect process because occupancy models are not perfect.
Application and conservation. Why monitoring populations matter. As humans, it is our role to monitor populations and try to protect the ecosystems that we love. Because of this, we need to have accurate population numbers so we know when to take action. Conservation success story. A story of success with conservation is the example of the peregrine falcon. The peregrine falcon was almost going extinct when researchers learned of its population numbers and took action. They took action by banning the use of DDT, an insecticide used in the 1970s that poisoned a lot of birds of prey, and by putting it on the endangered species list in 1972. Because of these actions today, the peregrine falcon is back at healthy levels and was taken off the endangered species list in 1999.
Below we have a linked Google Doc with all of our sources, an interview cited in MLA format.